All right, ladies and gentlemen, today's class recording has started. So, yesterday, we talked about that our next unit is going to deal with thermal energy. And whether you see it at this point in time or not, thermal energy is kind of a good bridge from the big scope world of things like basketballs and people and airplanes and trains to the small scope world of atoms and molecules and protons, neutrons, and electrons. So we're going to use this sort of to bridge the gap. So yesterday we introduced two terms that a lot of times sound similar but are in fact different. So first one we introduced was heat. What is our definition of, when we talk about thermal energy, what are we concerning ourselves with? What is thermal energy based on? Timmy, go ahead. The movement of atoms that make up an object, the small particles that make up that object. And so in relation to that movement, there's a couple of terms we talked about. So the first one was heat. What is our definition of heat? Frank, go ahead. Transfer of thermal energy because of a temperature difference. And we said that, Frank, in the fact that it's a transfer of energy, heat is a lot like what work that we talked about in the last chapter of changing that energy around. Heat, energy flows because of a temperature difference. Which way does energy flow, Frank, because of a temperature difference? Well, energy will flow from what object to what object? You want to pull somebody in on this one? Joanna, go ahead. High temps to low temps, right? We said hot things will cool down, cool things will heat up, and we used the example of the billiard balls when they run into each other, which one slows up, which one slows down, which one speeds up to illustrate that fact, right? So heat is a transfer of energy because of a temperature difference. The other thing we talked about yesterday was temperature. So what does temperature tell for us? What is our definition of temperature? Right? Christina, go ahead. The average kinetic energy of the particles, which basically is telling us what about them, Christina? If it's averaging kinetic energy, that's kind of indicating what for us? The velocity of those particles, or how quickly they move, right? Higher temperatures, higher velocity, lower temperatures, lower velocity. Okay? Good there? All right. But this unit deals with thermal energy. So let's talk about what thermal energy is. We said that it is related to the motion of the particles, but our actual definition is the total amount of motion of all the particles that make up that object. The total motion. Temperature tells us an average. Thermal energy gives us the total amount. And as a result, because it's the total motion, right, that's the total damage we can do, or the total amount of change that we can cause. So, what are some things that thermal energy is probably going to depend on? What's going to determine the thermal energy of an object? Temperature, definitely, because temperature is going to tell us how fast the particles move on average. But if we're talking about the total amount, what else are we going to need to know? That tells us that's temperature, right? Okay. Temperature tells us how fast the particles move on average, but if we want the total amount, right, what else are we going to have to know? Let's talk about, right? No. Let's talk in general terms, right? We can know, easy. Right? Let's say that, whatever, let's pick a fast food restaurant that we want to talk about.
Subway.
McDonald's is so...
Let's
go. How about Wendy's? All right, Wendy's. Does anybody not like Wendy's? How do you not like Wendy's?
I don't eat Wendy's anymore.
All right, so anyway, you go to Wendy's because you have to get yourself a junior bacon cheeseburger. Right? Whoa. After I teach you Italian pie, now you're going to miss the junior bacon cheeseburger?
If it was from,
It's like the best sandwich
if
ever.
it was from, Five
Gecko.
Guys, then I'd be like, yeah.
Five Guys is a little bit, I mean, yes, but sometimes you don't need a Five Guys. Well, you probably
I
always
need
need a
Five
Five Guys hamburger. Like, I just need a little snack. I'll go to
Need
Five
two
Guys. Like,
bacon.
if I eat Five Guys, that's basically all the food I need for the entire day. Like, that's, so. Anyway. Quickly stop this. I believe the first thing that happened was you hit him in the stomach. That's the first thing that happened. So. And it's on recording, so if your mom tries to come, I'll be like, no, this is what happened. So, anyway. All right, so you go to Wendy's to get yourself a junior bacon cheeseburger. Junior bacon cheeseburgers cost 99 cents. Actually, they cost a little more than that now because of inflation, but 99 cents, right? So you go to Wendy's and you buy 5 junior bacon cheeseburgers, right? Because you're just going for a little snack, you know, right? Your total bill is $4.95. How did we get to the total bill being $4.95? What do we need to know in order to get our total bill? We need to know how much what? We need to know how much each sandwich costs, right? But then also, how many sandwiches do we have, right? So, for thermal energy, the temperature tells us how fast each particle moves individually, but what else are we going to need to know if we want the total amount of motion? How many particles are there, right? So, right, thermal energy depends on 3 things. 1 is temperature, 2 is mass, right? And then 3, your book says this, but I think it's kind of redundant. Your book says it also depends on the state of matter, okay? Which, in a lot of ways, is the temperature, right? So, in your outline, the 3 things that determine the thermal energy, 1 is the temperature, 2 is the mass, and then 3 would be the state of matter. What, like I said, I think state of matter is basically related to temperature, so I think that's kind of redundant, but whatever. Okay? That's the total amount of energy, the total amount of change that we can do. Okay? Good? All right, so let's talk about these, this bucket and this teacup, which you have a picture of, right? Okay? So before we answer the question, okay? Before we answer the question that's related there, let's take a look at this this teacup and this bucket. So based on observations, what are you going to say here about these 2 things? What's one observation you can make by looking at these pictures?
The teacup is
The teacup has a higher temperature, right, than the bucket, right? But what other observation could we probably make? There's more water in the bucket, right? Is it possible for those, so, do they have the same temperature, at least based on this discussion, or based on this picture? No. And what is that telling you if they don't have the same temperature? If the cup has a higher temperature than the bucket? Tim, go ahead. The average kinetic energy is different. So what would we say about the particles in the teacup versus the bucket? They move faster. Okay? Does that make sense? We'll go with that. Okay. Is it possible for the bucket and the teacup to have the same thermal energy? Yeah. Right? Because thermal energy depends on 3 things. They both have the same state of matter, so let's get rid of that one, right? The teacup has a higher temperature, but the bucket has more particles, right? So thermal energy, the total damage that can be done, or the total change we can cause, right, depends on multiple factors, right? So let's take a look at this, right, on your sheet. It says, the water in the bucket and the water in the cup have the same temperature, even though it doesn't appear that way from the picture. Let's say they do. If they have the same temperature, what does that mean? First question I got.
Same velocity.
Same average kinetic energy. Or if we want to get into more of a description, right, that means what can we say about the particles? They move the same speed, right? Okay, so you have, like I said, you have these pictures on your outline, all right? And the first question is, if the cup and the bucket have the same temperature, what does that mean? It means they have, on average, the same kinetic energy, so that particles move, on average, the same speed. And if that was the case, which one would have more thermal energy? The big bucket, right? If they were the same temperature, we could do more damage, like, burning somebody, even though we shouldn't do that, right? We could burn somebody more with a big bucket of boiling water than we could with a little teacup of boiling water. You shouldn't burn anybody anyway, right? But, we could. Not that we should, we could. All right, let's take a look at the second picture. And the second picture is not something that's relevant right now because we're in the middle of winter, but let's take a look at some sparklers, right? So, individually, the sparks of the sparkler, do they have a high temperature?
Yeah.
Have you ever gotten one of those sparks on your hand before?
Yeah. It hurts.
Yeah. So they have a high temperature. And what does that mean about the particles individually in that spark? They're moving very fast. But does each spark of the sparkler have a lot of thermal energy? No, because there's just not that many of them, right? Or there's not that much of them, right? So, right, you have the sparkler picture there, right? First question, do the sparks have a high temperature or a low temperature? High temperature, what does that mean? Particles move very fast. But then the second question, do they have a lot of thermal energy? Not really. Why? Not a lot of mass. So again, make sure that we know our definitions, right? What does it mean to say something has heat, or what do we describe heat? What are we describing? When we say temperature versus thermal energy, all those things kind of sound the same, but they all have specific definitions. Okay, good there? All right, finally, thermal expansion and contraction, okay? I'm assuming most of you are familiar with the term of expansion and contraction, right? When we say expansion, that means it's getting what? Bigger, and then contraction is smaller. How does the temperature affect the volume? Because expansion and contraction affects the volume, right? How big something is, how small something is. So how is temperature related to the volume? Generally speaking, the higher the temperature, the more volume, right? So, based on the motion of the particles, the volume of the object will change. Based on the motion of the particles, as the temperature changes, the volume will change, right? And Frank, like you said, as the temperature increases, generally speaking, what happens to the volume? It increases, right? Okay? Because those particles take up more space. They move more. They take up more space. So as temperature increases, motion increases and volume increases. And then as temperature decreases, what happens? Motion decreases and then volume decreases as well. They're all direct relationships. Very good. And, right, this picture right here illustrates, you guys don't have this picture on your outline, but it illustrates the idea of thermal expansion and contraction. Okay? In this spot right here, we have a solid. Okay? Here, liquid, and then here, gas. Each of those has the same number of particles. But because the temperatures are different, the volume is different. Gases take up more space because they move more. The number of particles may be the same, but they move more, so they take up more space. Okay? Good there? So, a couple of applications of this, right? Okay, actually, let's talk about this sad situation. It may not happen to you much now, but maybe when you were a kid, did you ever go to a restaurant that gave out balloons?
Yeah, Red Robin.
Red Robin used to give out balloons. I don't know if they do anymore. So, yeah. Applebee's used to give out balloons too. They don't anymore.
We should just let them go.
But
Mac and cheese there is
so Frank, you hate Wendy's and you hate Red Robin.
And so is their,
I like Wendy's. I hate the new season Dairy Queen.
Dairy Queen. Like the food at Dairy Queen, Frank, or just
No, that's like the
Ew,
worst.
Frank.
That's like the worst.
Frank, oh my god.
I totally thought I was gonna say. Oh, so let's say when you were a little kid, you got to go on a night out with your parents, right? You went to Red Robin, maybe you went to the zoo or something. Who knows? It's a good day, right?
Yeah.
So you got home, you were exhausted, and your balloon from Red Robin got left in the car, right? But what happens to the temperature in your car overnight, especially in the wintertime? It decreases, right? And so what happens to that balloon, right? It gets all look at it. It's so sad. So sad over there. Like doesn't that guy look sad in the picture? Because his balloon has decreased in volume. All right? So what? Though they are definitely the same person. So summer versus winter, right? So, to illustrate the different temperatures. So, does anybody have an old school thermostat in their house? The one that you actually have to like turn the dial, or maybe maybe your grandma's house. I'm not saying your grandma lives in an old house, but that most thermostats today are electrical. But in an old school thermostat where you actually had to turn it, inside of that thermostat, there's a coil of wire. And the coil of wire expands and contracts as the temperature changes in your house. So as it gets, in the summertime, as it gets warmer, that coil of wire expands and expands and expands, and eventually gets to the point where it hits a switch. And what does that switch do? Turns on the AC. And then as it cools down, right, what's going to happen to the coil of wire? It's going to shrink. And as it shrinks back together, as it contracts, what does it do? Turns off the switch, right? So that expansion and contraction we use for temperature control. Or, right, you ever see one of these things on a bridge that either if you drive over or sometimes you go to Metro Park's big bridge, right, it has the little TV things at the beginning. Those are expansion joints. What happens to the bridge in the summertime? It expands. It gets bigger, right? It really does. And as a, what? Well, see these expansion joints right here? Right? As they expand, what do you think is going to happen? Right? It's going to get bigger and bigger and bigger. And you have to make the space big enough to account for all of the expansion of the bridge, right? But then in the wintertime, what happens? Right? It shrinks back up. So we have to, if we don't build in space for the bridge to get bigger and smaller with the temperature, right, we risk that bridge breaking. Right? And that's not good when bridges break, regardless of what size they are. Okay? Here, unfortunately, this happens to us now more and more in the summertime as temperatures or as climate is starting to become a little bit tending towards hotter and hotter things, right? Okay? Or if you go to the desert, you see the ground and it looks all cracked like that. Okay? There's moisture in the ground. But as that moisture gets warmer, what does it do? It expands, right? And it leaves these cracks in the ground. So when it gets really, really dry, right, that moisture leaving and expanding causes cracks in the ground. Right? Good with expansion and contraction? All right. Just to give ourselves a little bit of a jump so we can do a little bit more practice, let's at least introduce this idea of calorimetry, and at least do the first couple pages on the outline that I gave you today. We'll talk about specific heat. That's important. So, because then tomorrow we can just do some problems and not have to like sit here and just listen to me talk the whole time. Then we can do a little experiment on Thursday. It'll be good time. All right. So, we talked about in the last outline heat, energy moving around, and we said that heat flows from hot stuff to cold stuff, right? Hot things get colder, cold things get hotter. But what do we see about the total thermal energy in that interaction? It's going to stay the same, right? Whatever energy the warm thing transfers to the cold thing, right, it's going to get colder, right? The other thing's going to get warmer, the total energy stays the same. So how much energy is actually moving around? That leads us into this idea of calorimetry, right? First, right? Sounds like calories. That's how we measure thermal energy, right? We think of it as something that we use to measure what's in food, and it's true, but we're measuring the energy that's in food. And your body basically turns that energy in food into heat, because like we're warm-blooded animals, you know, but then also like into movement and you running up the stairs or whatever it is that you do, play tennis or whatever, right? So, and then the metry part, right, is the measurement. So how much heat are we measuring, okay? So, one big idea that determines how much energy is moving around is specific heat, or sometimes it's referred to as the specific heat capacity. So, by definition, specific heat is the amount of energy needed to raise the temperature of 1 gram of a material by 1 degree Celsius. The amount of energy needed to raise the temperature of 1 gram of material by 1 degree Celsius. So how much energy do we have to put into this thing to get the particles to move fast enough to raise the temperature by 1 degree Celsius? Okay. Materials that have lower specific heats have temperatures that increase or decrease by a greater amount per energy. So the lower a material's specific heat, the more the temperature will rise when a given amount of energy is absorbed. But it also works the other way too. The temperature will fall when energy is released. So I have it in terms of, you know, making something hotter, but it works both ways, right? So the lower specific heat something has, the faster that the temperature changes, whether we're heating or cooling. So things with lower specific heat values are easier to change the temperature of. Okay? All right, good there? Let's look at some examples that illustrate this, okay? So here's a guy eating a piece of pie, but I like to use this example because it's the best example of specific heat. It's the best example of specific heat I could think of. Why? Smack him in the face. All right, so you go home from school, and you know, it's been a long day, so you need a snack, right? So you look in the freezer, and what do you find? Mom bought pizza rolls when she went to the store, right? So pizza rolls, right, are the most deceptive things ever invented, right? In that the following things happen every time you eat a pizza roll, right? Throw those bad boys in the microwave for whatever, 2 minutes, right? You know, they come out, they're all steamy, right? So you let them sit there for a couple minutes. You like grab one, you're like, oh, this is ready to go. You pop that bad boy in your mouth, you take a bite, and what happens? No. It basically releases lava into your mouth, right? Have you ever eaten a pizza roll before? Right? Isn't the inside of the pizza roll always like tremendously hot? even though the outside is right. Okay. So when we look at the pizza roll, it's made of two parts. It's got the crusty outside, but it has the saucy inside. Right? Those two things have different specific heat values. Right? The crust has a low specific heat. So it heats up pretty quickly in the microwave, but it also cools down pretty quickly when you take it out of the microwave. Right? The sauce has a higher specific heat. So while you may, one of the things that happens sometimes, and this happens with toaster strudel, if you ever have toaster strudels, right? You put it in the toaster, you cook it, you pull it out, the crust is like, ooh, hot, and you gotta put it down on the plate, right? And you bite into it, and the inside, still cold, right? No toaster strudel? They aren't, but Pop-Tarts aren't good for you either. But, man. But she'll let you eat. She'll let you eat Five Guys for a snack, or do you have to like? You have to sneak that in. You have to sneak. I just want to let you know it's on recording now, so I can.
Yeah, Mom, you hear that?
Wow. How did it go from my mom won't let me eat toaster strudels to my mom makes bad food?
No, you don't make bad food.
Alright, so.
Mom's like close to a vegan. She's like on the verge of being vegan.
She probably doesn't like Five Guys in that time. So, yeah. Alright.
She takes the grease off of the grease.
Oh, it's my mom, but
She
Let's take
takes
some
it
napkins. I mean, that's one of the reasons. Like that's I don't like greasy pizza like that. I'll agree with her on
You
that.
gotta have taste.
Taste comes from the things that are on it, not the grease.
Grease is so good.
No. That's why I don't really like Pizza Hut.
That's why Five Guys.
So,
Pizza
yeah.
Hut is so bad.
Pizza is terrible. Pizza Hut is so not good. Papa John's is all right.
Papa John's.
We usually go to Teresa's. There's a Teresa's pretty close. It's kind of a local place. So. So, going back to the pizza rolls, right? The inside of that pizza roll stays warm longer than the crust because it has a higher specific heat. Things that have higher specific heats are harder to heat up, but they're also harder to cool down, right? Same thing with the toaster strudel example, right? The crust of the toaster strudel may have gotten warm, but the inside may not have cooked because the crust has a lower specific heat than the inside part does. Okay? Let's talk about another example, right, that is not relevant to us right now, but it'll make us think of days to come, right? So, you go to the beach in the summertime, right? I know it seems like a long time away, but it'll be here before we know it, don't worry. Go to the beach, right? And you're sitting there underneath your umbrella, right? Maybe on a blanket. Psst. Please, can we keep our hands to ourselves?
Yes.
Right? This is the kind of thing. This is the reason why I don't teach middle school, because I don't want to have to deal with this. All right. So please stop. So that's right. I just said you were acting like a middle schooler and you laughed. Not something you should be proud of. But you're no better. Just for the record. For the record. All right. We're at the beach. Sit underneath your umbrella, right? Reading a book, maybe, whatever it is, okay? And you decide, it's getting a little warm, I'm going to walk to the water and cool off a little bit, alright? So, you stand up, you take one step out from under the shadow of the umbrella, and what does the sand feel like? Basically like the surface of the sun, right? Okay? So, you run, blah, 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 you get to the water, you stick your feet in the water, now we're good, alright? The sand got hot, it's been sitting in the sun all day, right? But guess what? The water's been sitting in the sun all day too, right? Why is the sand hot, but the water isn't?
Specific heat.
different specific heat values, although the state of matter does play a little bit of a role there, but let's talk about specific heat, right? So, the sand gets hotter than the water. Why? Because it has a lower specific heat value. Things that have lower specific heat values are easier to heat up and easier to cool down. So the sand gets really, really hot in the daytime. But then if you go and walk on the beach at night, right? What does the sand generally feel like? Nice and cool, right? Because it gained all that energy from the sun during the daytime and got really warm and its temperature got really hot. But then at night, it loses all of that energy and cools down. We think of the desert as being a really, really hot place, but what happens in the desert at nighttime? It actually gets really cold, right? Because sand, low specific heat, gets really hot during the day, but it cools down really quickly at night. Okay? All right, good there? All right, we will pick it up from here tomorrow, and we'll do some calculations, some sample calculations, and then we will experiment on Thursday. That is our plan. Oh, if you take a look at the calendar, there are some reading assignments on temperature, and then there's also some homework assignments on temperature, heat, and thermal energy. You might want to check those out just to, make sure we got those things down.